Okay, in this video we're going to talk about the limit comparison test. And in this first video about the limit comparison test, we will talk a little bit about the theory. So this test, as I said at the conclusion of our previous video, this test is going to be really useful when we have something that looks like a power of n, but where we can't really ferret it out exactly. So that's going to be the family of examples where it's useful, and let's go ahead and take a look at what the theory tells us. Okay, so the limit comparison test, we start with an and bn non-negative terms, and we suppose that the limit as n goes to infinity of the ratio of the terms is some constant that's non-zero and is actually a finite number. So then if that limit is equal to a constant c, that means that for large values of n, an looks like that constant times bn, which means that if n here is very large, on the tail of the series, the two tails are going to be roughly proportional. I mean, that's really a very heuristic kind of statement, but it's a useful way of thinking about it. So then the upshot is, if you have that the limit of this ratio is this constant that's neither 0 nor infinity, then the series an converges if and only if the series bn converges. Right? So that means that an converges if bn converges and an diverges if bn diverges. But what we're going to look at now is some examples where this is a useful point of view. So let's start with this example that looks horrible. It looks like n cubed minus 6n squared plus 22n over 17 over n to the fourth plus 5n minus 4. And we're taking the series of this n equals 1 to infinity. Okay, that one looks absolutely horrific. But it's going to turn out to be reasonably nice by the limit comparison test, because what we do is we identify what is the dominant term in the numerator. Well, we have n cubed minus 6n squared plus 22n minus 17. So the dominant term is this n cubed. And then we have a dominant term in the denominator. Well, here we have n to the fourth plus 5n minus 4. So there the dominant term is n to the fourth. So this whole fraction, we expect it to behave like roughly n cubed over n to the fourth, at least for large values of n. And that's just 1 over n. So what we're going to do is we're going to compare our series to the series whose term is 1 over n, like the harmonic series. And the harmonic series diverges. So what we need to do is we need to figure out to what extent this comparison is reasonable. So for that, we're going to take the limit as n goes to infinity of our thing, right? That's n cubed minus 6n squared plus 22n minus 17, whole thing over n to the fourth plus 5n minus 4. And then we're going to divide that by 1 over n. Right? This is we take the ratio of the terms of the two series, and we look at the limit of the ratio as n goes to infinity. Well, this is then the limit as n goes to infinity. Okay, remember when I divide by a fraction, that's multiplying by the reciprocal, so that's just multiplying this thing by n. So that becomes n to the fourth minus 6n cubed plus 22n squared minus 17n, whole thing over n to the fourth plus 5n minus 4. And now the limit of this as n goes to infinity, we're just going to get the ratio of the leading terms. So that limit is going to be 1. Okay. So then by the limit comparison test, by limit comparison, the first series, right, our series converges, and this is maybe more detail than is necessary, but just to make it clear, right? Our series converges if and only if the harmonic series converges. But we know that the harmonic series diverges. And hence, our series diverges. And that's the use of the limit comparison test in determining if a series like this converges or diverges.